Golden Iris Productions presents The Question That Broke Physics. Why is light always the same speed? By Mark F. Dennis. For centuries, motion seemed simple. If one object moves toward another, their speeds should add together. If they move apart, their speeds should subtract. This idea works for everyday experience. But when scientists began studying light, they discovered something astonishing. No matter how fast an observer moved, light was always measured at exactly the same speed. This simple fact created one of the greatest puzzles in the history of physics. The puzzle. When Einstein introduced special relativity, many people struggled to understand it. Imagine two observers moving in opposite directions. A beam of light passes by. Common sense suggests that one observer should measure the light moving faster, and the other should measure it moving slower. Yet both observers measure exactly the same speed. How can that be? Maxwell's insight. The answer begins with James Clerk Maxwell. Maxwell unified electricity and magnetism into a single theory. His equations revealed that electromagnetic waves travel at a speed determined by two fundamental properties of space: the electric permittivity, epsilon naught, and the magnetic permeability, mu naught. Together, they define the speed of light. This suggested that light is not behaving like an ordinary object. Its speed is built into the structure of space itself. A radical idea. Light does not behave like a baseball or a train. Its speed does not depend on the motion of the source. It does not depend on the motion of the observer. Instead, its speed is determined by the properties of spacetime. This was a radical idea, and it laid the foundation for Einstein's revolution.
A simple question. Consider a photon leaving a distant star billions of years ago. It began its journey long before humanity existed, long before any observer was present to measure it. When that photon finally arrives on Earth, we measure its speed and find that it is moving at c. Did our observation somehow change its motion? Of course not. The photon was already traveling at c throughout its journey. The missing piece. At first glance, this seems to create a contradiction. If different observers assign different positions to the photon, does that mean the photon exists in two places at the same time? No. The mistake comes from assuming that everyone shares the same universal time. Relativity tells us that they do not. Different observers divide space-time differently. Each observer measures the speed of light as c. Not because the photon changes, but because space and time are measured differently. When light cannot reach us. Motion alone does not prevent us from receiving light. Even a galaxy moving at 95% of the speed of light can still send light that eventually reaches us. But there is another effect, the expansion of space itself. If space expands rapidly enough, light can be carried away faster than it can travel toward us. The result is a cosmic event horizon, a boundary beyond which light can never arrive. Relativity's answer. The speed of light is not something baked into the photon alone. Instead, space-time adjusts. Space adjusts. Time adjusts. As a result, every observer measures the same speed of light. This is the central insight of special relativity.
Where motion appears. Motion has not disappeared. It simply shows up somewhere else. Instead of changing the speed of light, motion changes wavelength and frequency. When objects move away from us, their light is stretched. The wavelength becomes longer. This is called redshift. But wait, a natural question follows. Could photons somehow have always been moving at the speed of light relative to us, even before we existed, even before there was anyone here to measure them? The idea sounds appealing, but it leads to new difficulties. A logical problem. If light was always moving at c relative to us, how do we explain redshift? Why would the spacing between wavefronts change? Why would distant galaxies appear shifted toward longer wavelengths? Clearly, something physical is happening during the journey. The answer cannot simply be that observation creates the effect. Another attempt. Perhaps the wavefronts stretch while the light travels, and perhaps only when we detect the light does it somehow become C in our frame. But this explanation raises even more questions. What was the light doing before we observed it? What determined when the change occurred? And why would every observer obtain the same result? Light's journey. The path of light through the universe is rarely simple. Light passes galaxies. It passes clusters of galaxies. It moves through regions influenced by dark matter. As it travels, its path can bend and curve. The universe acts like a giant optical system.
Gravitational lensing. One of the most beautiful examples is Einstein's cross. A single distant galaxy appears in 4 different locations. The galaxy has not been duplicated. Instead, gravity bends the paths of the light. The path changes. The speed does not. Extreme distances. Consider the galaxy known as GNZ11. Its light began traveling more than 13 billion years ago. As the universe expanded, that light was stretched into the infrared. What we see today is a snapshot of the early universe, a message from a time close to cosmic dawn, an expanding universe. The story does not end there. That galaxy continues to recede. Today, it is much further away than when the light began its journey. In fact, some new light emitted by that galaxy may never reach us at all. The expansion of space has become too great. A remarkable truth. Throughout all of this, light can bend. It can stretch. It can be delayed. Its path can become enormously complicated. Yet whenever it is measured locally, its speed is always found to be c. That consistency is one of the deepest facts in nature. Not so strange. At first, relativity seems mysterious. But it is not magic, and it is not mysticism. It is a logical consequence of how space-time works. An analogy. Think about sound. When a source moves, the pitch changes. The frequency changes. But the speed of sound through air remains the same. Something similar happens with light. Motion changes wavelength and frequency. The speed remains constant. Einstein's insight. This was Einstein's great realization. The speed of light remains the same because space and time themselves adjust. Observers moving relative to one another do not agree on measurements of distance. They do not agree on measurements of time, yet they all agree on the speed of light. One space-time, different views. Imagine 2 aircraft crossing paths. Each pilot considers themselves at rest. Each sees the other as moving. Relativity works in exactly this way. There are not multiple spacetimes.
There is only one space-time. Different observers simply divide it differently. And for every observer, the light cone remains unchanged. The space-time picture. To visualize this idea, physicists use a space-time diagram. Space is shown horizontally. Time is shown vertically. A flash of light spreads outward at the speed of light. Its path traces a 45-degree line. This simple picture reveals the structure of causality itself. The light cone. Light can move in 2 directions, forward through space or in the opposite direction. Together, these paths form an X-shaped structure called the light cone. Inside the cone are events that can influence one another. On the edge lies light itself. Outside the cone are events that cannot be reached without exceeding the speed of light. What we learned: light always travels at speed c, not relative to a source, not relative to an observer, but as a property of space-time itself. This is one of the fundamental principles of modern physics. The deeper question: if every observer measures light the same way, then what actually changes? The answer is not the light. The answer is space and time themselves. That realization transformed physics forever. Final thought: the mystery is not the photon. The mystery is not the beam of light. The real mystery lies deeper. It is the nature of space-time itself. And that question continues to inspire physicists today, because understanding light ultimately leads us to a deeper understanding of reality itself.